Alright, so we're going to continue here exploring the idea that electromagnetic waves are the same thing as light. And to make our diagrams a little bit easier, we're going to introduce the concept of what is a plane electromagnetic wave. And this is a wave where the fields are uniform over any plane perpendicular to the direction of propagation. So you can think of, I usually tend to think of them as a bunch of rectangles marching forward. And they represent essentially the magnitude of the field at that particular spot. So what I've drawn here, and my three-dimensional drawing is never the greatest, but you can see an electric field in the y direction, a magnetic field in the z direction, and the wave is propagating out in the x direction. So this field would, the plane of the plane wave would be in the zy plane, and that plane would march forward in the x direction. And keep in mind, while I've only drawn one rectangle, there would be many multiple rectangles as extending back, representing the wave, well, the entirety of the wave. So the first thing we're going to do is put our wave in a Gaussian pillbox, and that Gaussian pillbox is going to extend in the front of the wave. So the front of the propagation of the wave is going to be, say, in the middle of the Gaussian pillbox. We are first going to apply Gauss's law for electricity to our propagating wave. And there's no charge enclosed, so that would imply that Q enclosed would be 0. So if we look at, and remember there's a Gaussian pillbox around this, the electric field is going to come in from the bottom of the box and go out the top of the box. So that once again, Q enclosed is 0, the electric flux is going to be 0 because we have in and we have out. Now remember, when we put this Gaussian pillbox around this system, we made it so that the start of the wave was in the middle of the box, and so there was empty box extending out front. And that means that we can't have the electric field come in the back of the box because it would not come out the front. So that means that the electric field cannot be in the direction that the wave is propagating in. Alright, so we're going to do the same thing, but now apply Gauss's law for magnetism. And we're going to have the magnetic field come through the side of the box and come out the front in the positive z direction. But once again, because the wave does not extend through the entirety of the box, if we had to come in the same direction as the direction of propagation, it would come in and not come back out, and that would not be 0, and we would have a problem. So this allows us to say that you can have the electric field or the magnetic field propagate in the x direction, where the x direction is the direction the wave is propagating. So that means that they have to be what we call transverse waves, where the electric field and the magnetic field have to be perpendicular to the direction of motion of the wave. And if they weren't, we would run into a situation where the electric field lines would come in or the magnetic field lines would come in and not go out, and the flux through the entire enclosed surface would then not be 0, when it would be in other situations, which is a violation of Gauss's laws. We're now going to discuss Faraday's law. So I've written Faraday's law down here, and I've rotated our system a little bit so that we can focus a little bit more in 2 dimensions. So this is the y direction with the electric field. This is the x direction, the direction that the wave is propagating in, and then the magnetic field is coming out of the page in the positive z. And now I have drawn a rectangle because for Faraday's law we need to integrate over some dl or over some path. And that's what I'm going to do in this particular case. So remember, we have extended this in front of the wave. So the side e to f is 0 for that particular side. For sides g and f and h and e, the electric field is perpendicular to dl, so we don't have to worry about that side. So the only side that is parallel and would have electric field going through it is the back of the rectangle, or side GH. And remember, we want parallel because we're doing a dot product here. So we're going to do the integral of E dot dl is going to equal negative because of the direction we decided to integrate from. The electric field times side A, which is going to be this G to H side. For the other side of Faraday's law, so we're first going to focus in on the change in flux. We have the magnetic field, and remember flux is magnetic field times area, so we need the area. So A, remember we decided was the side of the box, and we're taking the idea that velocity is equal to distance over time, rearranging to solve for distance. So you get a velocity, c, and time. So this is essentially the amount that the wave is moved forward, or the box is moved forward with the wave. We can then divide both sides by dt, getting rid of this dt here, and then setting this half of Faraday's law equal to this half, which gives you this relationship here. And technically speaking, there should be a minus sign here, because I forgot to write the minus sign down for that half of Faraday's law. So that would cancel out this minus sign over here, the a's cancel out, and you're left with this relationship here. So this tells you the relationship between the magnitude of the electric field and the magnetic field, and the magnitude of the magnetic field. Now we're going to apply Ampere's law. So we've written Ampere's law here. There's no wire through our setup here, so the conductive current is 0. And we're actually worried about the displacement current. And so this gives this relationship here. So I've rotated our setup here again, where this is the x direction, and I put the z direction down in the negative y direction, so that the positive y is coming out of the page. So you have the electric field here coming out of the page. We have the magnetic field down here in the positive z direction. And once again, we've drawn our box. So we're going to start with the integral of B dot dl. Once again, E side E and F is in front of the wave. FG and HE, the magnetic field is perpendicular to dl. And once again, this is a dot product in here, so we only want the parallel components of B. B and L have to be parallel to each other. So that means that the only side we're worried about is this GH side back here. So our integral of B dot dl is going to equal side GH, which is going to be the magnetic field times what we're going to call the length A, because we define this side as A. Now we're going to do the other side of Ampere's law. So we're going to start with the change in the electric flux. Remember, electric flux is electric field times area. So we have the electric field here, and once again we're defining the area where this side is this side of the box, and then this side is how much the wave has propagated forward. So we get this move forward by taking the velocity times the change in time. Once again, we divide by the change in time on both sides to be able to set up the electric flux changing with time. And then we set the two relationships equal. You got to remember these constants out front. And we end up with this relationship here. I can take this relationship here and sub it with this relationship here, and I end up with this, telling us that the velocity of the wave is propagating forward is equal to the square root of the electric constant times the magnetic constant. And if you actually take out your calculator and do this calculation, you find out that c is equal to the speed of light. And notice we have the little knots here. Those knots always mean that you're traveling in a vacuum. So that means that the speed of light travels, or this wave propagates with the speed of light in a vacuum. All right, so what did we learn? So let's talk about the key properties. The first is that the wave must be transverse. So B, the electric or magnetic field, and E, the electric field must be perpendicular to the direction of propagation, or v, and they must be perpendicular to each other. And that is told to us by Gauss's law. We also discovered that the magnitude of the electric field is equal to the speed of light times the magnetic field. And we learned that through Faraday's law. And then finally through Ampere's law, we learned that the speed of the wave, which we're going to call the speed of light, is equal to 1 divided by the square root of the electric constant times the magnetic constant. And so this is going to be a constant in vacuum. And that's going to equal 3 times 10 to the 8 meters per second. Alright, so the last thing I want to go over in this section is the right-hand rule of being able to establish the direction of the electric field, the magnetic field, and the propagation of the wave. So you're going to put your thumb in the direction of the propagation. You're going to put your fingers in the direction of E, so you're going to put your fingers in the direction of E, and then you're going to grab the magnetic field. And you're going to have to curl in order to be able to grab the magnetic field. So you're going to curl your fingers. So thumb in the direction of E, point your fingers in the direction of E, and then curl your hand to grab the, essentially the point of the end of the vector that represents B.